So the galactic center is a region. Um, if you look in the night sky, of course, it's part of the Milky Way, and it's actually part of the Milky Way that's thickest. It turns out to be in the direction of Sagittarius. It just happens to be in that particular direction of the night sky. Anyhow, um, uh, we can't actually see the center of the galaxy because there's too much gas and dust between us and the center. And at least we can't see it in the visible part of the spectrum. But of course, we can see it in radio waves and in infrared. In some cases, in X-rays, and we do have some evidence of what's going on in the center of the galaxy in terms of gamma ray observatory and gamma ray observatory. Remember, X-rays and gamma rays don't penetrate the atmosphere, so those are space telescopes. All right. Let's see. What does this do? I want to talk about this. All right. So one of the things that we find is, and this is very the main thing that we find at the center of the galaxy, besides the fact that there are lots and lots of stars at a relatively close distance to each other, much greater density than we find it way out here in the spiral arms, and in the middle of the spiral arms, like we are. So besides that, there is this region which gets the designation Sagittarius A star, which is a region that that's the point where we think the supermassive black hole is. Okay, so its diameter is really tiny. It's only about 10 astronomical units. So if you think about it, that's smaller than the solar system, right? So this is an incredibly small but very massive object there. And the mass of the object is around, I think the first estimates put it around 5 million times the mass of the sun. I think it's actually closer to about 4 million. The more modern estimates put this supermassive black hole at about 4 million, 4 times 10 to the 6 times the mass of the sun. All right, so it says it may occupy. People don't really dispute that anymore, and you're going to see that there's overwhelming evidence that there is this supermassive black hole. Not just in the center of our galaxy. It turns out the center of all galaxies have a supermassive black hole, and the supermassive black hole is not just. So let me describe the name. Let's go over the name before we move on any further. Traditionally, the thing that is a black hole is a massive star. Usually starts its life 10 times the mass of the sun or greater, and then collapses into a supernova. And then, if what's left, you might recall from I think it was chapter 15. If what's left is 3 times the mass of the sun or greater, then not even neutron degeneracy can hold up such a star, and it collapses in on itself. So what we call that now is a stellar black hole. So a black hole that is just caused by a single star, right? A single event in the galaxy, in other galaxies. But the evidence for black holes at the center of galaxies actually is not very old. It's less than 20 years old. This evidence. I mean, we really didn't even know. When you go back 20 years ago, we didn't know that there were these supermassive black holes at the center of the galaxy. All right, so this is data that was taken in the infrared from a very famous telescope called there's 2 telescopes called the Keck observatories. They're these twin telescopes in Hawaii and on top of Mauna Kea. At any rate, we see. So what? Let's go over what you're seeing here. So this is, of course, the direction of the center of the galaxy, in the direction of Sagittarius, and we see several stars that are in orbit in very, very, very tight orbits, and the orbits are some of these orbits are only lasting for just a few years, but then some of them are much old, take a lot longer to orbit. But what they do is they're all orbiting a point. See where this this star is right here? They're all orbiting that point. So these are the stars really close to the center of the galaxy, all seem to be orbiting a single point, and there is, nothing there in the visible part of the spectrum. Good candidate for a black hole. Now, of course, what you do is you can figure out what the mass of that that star is right there. The star thing there is just an animation. That's not actual. That's just showing the point where everything is centered. All the orbits center on that point. At any rate, you can figure out what the mass of that star is, that supermassive black hole, and by just doing the modified version of Kepler's third law, right? So you take one of these stars and watch the orbit, figure out what the semi-major axis is and what the period is, and you can calculate what the mass is that the star is orbiting. And it turns out to be anywhere between about 5 million times the mass of the sun to about 4 million times the mass of the sun. More and more evidence is showing that it's actually closer to 4 million times the mass of the sun. All right, but 5 million times the mass of the sun is perfectly fine. Let me actually go back to this idea of supermassive black holes again. And what we're going to find out, and not in this chapter, but in the next, is that, as I said before, all galaxies have these supermassive black holes. Now, ours is only about 4 million times the mass of the sun. There are some galaxies that have supermassive black holes that are billions of times the mass of our sun. Okay, so ours is only 4 million times the mass of the sun. Ours is actually kind of a small supermassive black holes. As far as all the supermassive black holes that we find and we measure, what their mass is, ours turns out to be pretty tiny actually, compared to the other ones. All right, so let's talk about the formation of the Milky Way. What we think. What some of the evidence shows. Of course, we weren't around 13 billion years ago, but we can certainly we know that there was a time when there was no population 1 stars, not even population 2 stars. Remember, population 2 stars have a little bit of their mass, a small fraction of a percent as metals. So there's actually another type of star. Remember, population 1 stars are metal rich, anywhere from 1 to 2% or more of their mass is made up of metals. Anything heavier than helium. Population 2 stars have very very small amounts of metal, less than 1% of their mass is made of metals. And so there must have been a class called population 3 stars. And population 3 stars would be original stars, the stars that originally formed out of the gas that was created during the Big Bang, right? And that would have been just pure hydrogen and helium, just just hydrogen and helium. That was all. So, and now we've never found any population 3 stars, at least not up to this point. We don't think that they exist anymore because, of course, even the most remote stars have had some kind of, I guess you could call it contamination. I don't know if that's a good word for it, but some metals have creeped in, because the winds, the explosions that are taking place, and these quote winds. It's not really wind, of course, not in the sense that we talk about on Earth, but particles traveling outward have had time in the 13 billion years since the Big Bang to have reached any remaining population 3 stars, that have not either gone supernova. Of course, the really massive ones would have gone supernova a long time ago. But let's say one population 3 star had just accumulated a small amount of mass, maybe even only about I don't know, a tenth the mass of the sun. Well, those stars should still be around, and we should still be able to see them. But the problem is that there's been other stars exploding all around, and there's been enough time in the universe for those population 3 stars to be what we would now call population 2 stars. Okay, so here's the formation. This is just a rough idea of the formation of the galaxy. You have the primordial gas and dust that comes from the Big Bang, and there's many of these gigantic clouds, many millions of light years across, scattered throughout the universe. The local one, of course, is what's going to become the Milky Way. You have stars forming. Of course, stars have to form first. Then what happens is we think really in the early universe, really even more massive stars than we measure today were undergoing formation, and so those stars would have undergone supernova explosions very quickly. Just within maybe a few tens of millions of years, maybe 100 million years at the most. And then as those stars went supernova, so you can already think about, if you think about that, if this happened certainly within the first billion years, the material from those supernovas have had time to distribute that material throughout what is to become the galaxy, right? And so, if you take some remote part of the galaxy where you had a population 3 star that just had pure hydrogen and helium, well, some of that supernova stuff, the exploding stuff that comes from the supernova, has found its way into these other stars. Even just a small bit. That's perfectly fine. As this cloud, which is 3-dimensional, begins to rotate and collapse, this is all what's called the conservation of angular momentum. It flattens out, and then the regions outside where there's these halo stars, which become what we call the globular clusters. By the way, we don't just see globular clusters around our galaxy. We see them around other galaxies as well. At any rate, those stars don't have time. I'm sorry, they have plenty of time, but those stars don't evolve the way the stars in the disk do. Right? The stars in the disk here, as the disk rotates around, you're getting stars, mixing up with other stars and passing their material between. They don't have to come into contact with each other or anything like that. They can be many light years apart, but there's a stream of material that ends up in these stars. And then when you have new supernovas taking place, then that material gets gets distributed, mainly in the disk of material, in the galactic disk, right? And so this is where most